So good evening everybody. It's a pleasure to be here to talk to MSAS this evening about dark matter. Now it's been known for quite a long time now that the universe has a dark side. It's virtually 100 years old, a little less than 100 years. Dark matter in that sense is not a recent problem that has just, if you will excuse the pun, come to light. Here's one way of looking at it. This is a cartoon in which a lecturer is saying after the discovery of antimatter and the discovery of dark matter, we've just confirmed the existence of doesn't matter, which does not have any influence on the universe whatsoever. I'm going to try and convince you that dark matter is important and does have an influence, a very important influence on the universe. So let's just remind ourselves about the composition of matter. What makes up everything that's in the observable universe? If we divide everything we know about between stuff we know about and stuff we don't, okay, somebody needs to be admitted. Let me just get rid of that window. Okay, if we divide everything into two categories, stuff we know about and stuff we don't know about, then we find that all of the material, all of the matter that we definitely understand only comprises about 16% of everything that's out there. That 16% we can subdivide, if we so wish, into, you might think most of it would be stars inside galaxies. Well, actually no. Most of the 16% of matter that we do understand is mainly hydrogen and helium, as you can see from this pie chart on the right. Somebody else in the room needs admitting?
I'll deal with that.
Yeah, I still get the banners coming up on my screen because I'm co-host, unfortunately. So on the right-hand pie chart, we can see that 13% out of everything is the hydrogen and helium. This is essentially the gas that's left over from the Big Bang. And you can see that stars actually only comprise a very small fraction of everything that we actually know about. The 1% there, I'm going to mention that later. That's another type of particle called neutrino that, although they are very lightweight, they actually make up a relatively large mass of the universe simply because there are so many of them. But the take-home message from the right-hand pie chart is that stars only make up 2% of everything. Gas, helium and hydrogen gas make up quite a large fraction, but what we're talking about here this evening is not stars and gas. What we're talking about is, what is this here, this 84%, what is that? So I'm going to be going through looking at the nature of matter and light and asking why is dark matter dark, and then we'll look at some strands of evidence. In this talk, in principle, there are 4 strands of evidence. I'm going to be looking at the first 3. The 4th one is included in a handout of the talk, and I'll make that available to you later. Then we'll ask the question, after looking at the evidence that it exists, we'll ask, well, okay, but what is dark matter? Having established that there is something out there, we then ask the question, what is it? And I'll finish with, does it matter? In other words, what are the consequences of the existence of dark matter? Or explicitly, what would be the consequences if it didn't exist? Okay, let me just get rid of that window again. So, excuse me, these windows keep popping up. So, excuse me. The window is getting a little bit annoying. Let's get rid of it. Okay, so why is it dark? So the simple answer to why dark matter is dark is, well, it's because it's not light, but that's a little bit facetious. It does not behave the same way as ordinary matter. So ordinary matter interacts through what we call the electromagnetic force. In other words, it absorbs and emits electromagnetic radiation. Let's just call it light from now on. It doesn't matter whether we're talking about light in the sense of optical light or infrared or ultraviolet or radios or gamma rays. Any part of the electromagnetic spectrum, normal matter interacts with light. And hence normal matter can be detected either by looking at the light, for instance, that's coming from stars, or we can see, for instance, dark nebula, because if there are bright objects behind a dark nebula, it will absorb some of that light, and so we'll see it in silhouette. But dark matter does none of those things. It doesn't emit and it doesn't absorb. We talk about dark matter, but a better description might be invisible matter, because it doesn't absorb light like ordinary matter would do. But it's too late now. The term dark matter has caught on for many decades, and so we're stuck with that particular name. So all of ordinary matter, or normal matter, is made of atoms. So a current picture of an atom is something like a positively charged nucleus, negatively charged electrons buzzing around, and because we have different electric charges, positive in the middle and negative on the outside, it's those electric charges that give rise to the electromagnetic spectrum, i.e. light. So anything that's made of atoms can emit or absorb light. So dark matter must be something other than a collection of atoms. That's the hypothesis. So let's have a look at the strands of evidence that tell us that dark matter exists. Strand of evidence number 1. We can look at galaxies in clusters, and we can ask the question, what holds galaxies together in a cluster? So we might see lots of clusters like this. This is just one chosen at random. Apart from one or two stars that might be in the field of view, most of what you can see here are galaxies. All of the fuzzy objects are galaxies, and you can see that there are perhaps hundreds, perhaps even thousands of galaxies in the same region of space. So we can ask the question, what's holding them together? And of course the answer is gravity. It's not a trick question. Gravity is keeping these objects together in much the same way that gravity keeps the stars in the galaxy and gravity keeps the planets going around the sun. Gravity, of course, depends on mass, and we can estimate the mass by looking at this large galaxy cluster in a number of different ways. But one way we can estimate the mass of the galaxy cluster is to measure the galaxy brightness. And then, assuming we understand stars, and in this talk I'm going to assume that we do understand how stars are born, how they live and how they die, and hence if we know how bright a galaxy looks, we can understand how many stars there must be in that galaxy. Some stars are brighter than others, but on average we can say the average star has a certain brightness. So if the galaxy has a measured brightness, then we know roughly how many stars it contains. And given, again, some stars are more massive than others, but we've got a pretty good idea of what the average mass is, and hence if we know how many stars are in a galaxy, we know the total mass of the stars in a galaxy. And hence we know the mass of the galaxy, once we take into account that there's some gas floating around there as well. So when we do this for all of the galaxies in a cluster, we now have an estimate for the total amount of mass in that cluster. And hence we have an estimate of the total gravity that should be holding that galaxy cluster together. But even as far back as the 1930s, getting on for 100 years ago, it was realized that the gravity that seems to be there to hold the galaxy cluster together is not enough to hold the galaxy cluster together. In other words, the galaxies should have drifted away a long time ago. We don't think we're looking at every galaxy cluster at a particular time before the galaxies have had a chance to drift away. So something must be holding them in place. So the question is, what is that? Something appears to be wrong if we estimate the mass from how much we can see in the galaxy cluster. So using the luminosity underestimates the total mass that is apparently there, and it underestimates it not by a small amount, not by a few percent, not by 10%, not by 20%. It underestimates the mass by a factor of 2, a factor of 3, a factor of 5, a factor of 10. The amount of mass that has to be there is much, much larger than the amount of mass that we can get by just looking and effectively counting stars. So here's an expression that's going to crop up more than once this evening. It's as if there is some additional mass that apparently must be present. It's not counted by counting stars. It doesn't appear to be luminous mass, but it's there providing the extra gravity that's needed to keep the galaxy cluster intact. It binds the galaxies together. What is this additional mass? We don't know. Let's call it dark matter, because that sounds pretty cool. In the very early days it was simply called the missing mass problem, but now everybody calls it dark matter. Let's have a look at a second strand of evidence which is independent from the first, but is similar in the sense that we're going to try and calculate what is holding a particular object together. In this case the object is not galaxies within a galaxy cluster. We're now going to look at stars within a galaxy. And we know that all galaxies rotate. And the question is, how fast are the stars moving? Because just like the Earth going around the Sun is held in orbit by the Sun's gravity, then if a star is orbiting a galaxy, it's being held in place by the gravity provided by the galaxy. So how do we measure how fast stars are moving? Well, we can use the Doppler effect. This is the effect whereby if we look at the spectrum of a star and we see, for instance, characteristic absorption bands, dark bands within the spectrum of the star, if the star is not moving towards us or away from us, those dark bands appear in a particular position, the same position they would occur in if we were to do a lab experiment. But if the star is moving away from us, those dark bands appear to be shifted towards the red end of the spectrum. And if the star is moving towards us, those absorption bands appear to be shifted towards the blue end of the spectrum. And the amount by which they shift tells us how fast the star is moving. So the cartoon on the right gives us an idea of how we can use this. If we imagine that we've got a galaxy spinning in what is indicated here as approximately the horizontal plane, then those stars on the left-hand side, labelled A, those will be moving towards us, and so the spectra from those stars will be shifted towards the blue end of the spectrum. And on the right-hand side, those stars are moving away from us, so light from those stars will be shifted to the red end of the spectrum. And by measuring these shifts, we get the velocities. So we won't use a galaxy like this face-on spiral galaxy. You can see that most of the stars will be moving in the plane of the screen that you're looking at. And so very few stars will be moving towards us or away from us. So we won't choose a galaxy that is face-on. If we want to get stars moving away from us or towards us, we need a galaxy that's tilted. If we're looking at it absolutely edge-on, you might think that's ideal because some stars are definitely moving away and some stars towards us. But notice this dust band that goes down the centre of the galaxy. That means a lot of the stars will be obscured from our view at this angle, and so that's not ideal either. We don't want them face-on, we don't want them edge-on. We choose a galaxy that's at a little bit of an angle, such as here M33. And I'm not showing individual spectra, but here's just a colour-coded indication of the fact that some stars will be moving towards us and will end up getting blue shifted. Other stars will be moving away from us and will be red shifted. I'm not implying here that the stars will look blue or the stars will look red. This is just a schematic to remind us that stars will be travelling in different directions and we should be able to measure those velocities. So the question is, what would we expect? In other words, if galaxies rotate the way we think they do, what would we expect when we measure star velocities? And in particular, how would they vary if we look at different stars at different distances from the centre of a galaxy? Well, we know what to expect for planets going around the Sun. In other words, the Earth is kept in orbit by a large gravitational body in the centre of the solar system, the Sun. The same is true for Mars, the same is true for Jupiter, etc. And we know what happens in that situation from the laws of motion that were observed by Kepler and explained by Newton. If we look at the orbital speed, how fast a planet is moving as a function of their distance from the centre of the solar system, the so-called semi-major axis, just treat that as the average distance to the Sun, you can see that Mercury, Venus, Earth, Mars are travelling quite quickly, but as we go out further into the solar system, the velocities of the planets is falling away and getting less and less. When we go out to Neptune, it's so far from the Sun's gravitational pull is relatively weak, and so the planet doesn't have to travel very fast in order to maintain its orbit. Whereas Mercury, a lot closer to the Sun, much stronger gravitational pull. Mercury has to travel quite fast to maintain its orbit. Rather than plot it in this way, we could plot it on a logarithmic scale, in which case the line becomes a very nice straight line, but we're not going to bother with that. We're just going to stick to this idea that the velocity should fall off like this the further away we get from the main object that is holding those objects into orbit. In the solar system, 99 point something% of the mass of the solar system is concentrated in the Sun. It's not quite the same for a galaxy, because the mass of a galaxy is not all at the centre. Well, there's a big massive black hole in the centre, but a lot of the stars, of course, are distributed throughout the galaxy. So we're not expecting to see exactly this. But we can plot out the velocity of stars that's measured as a function of the distance those stars are from the centre of this galaxy. It doesn't really matter which galaxy this observation is for. If we're looking very close to the galaxy, remember this scale is clearly tens of thousands of light years, rather different scale to the one in the solar system. But if we're talking about stars that are relatively close to the centre of the galaxy, these stars, you see, the velocity is going up. Because remember, most of the mass is not concentrated absolutely in the centre of the galaxy. If we go out to a distance, let's say 5,000 light years, roughly where my cursor is, a lot of the galaxy is inside that orbit, holding the star in orbit, but of course there's quite a few stars outside of that. So we really have to go to 10, 15,000 light years before we can start to say, well, look at that red circle or that red ellipse. Most of the galaxy looks like it's inside that red circle. We've just drawn an arbitrary line saying 99% of the galaxy appears to be inside that red outline. So when we look at stars that are further away than that, beyond this yellow curve that we've seen here, surely we must get to the same sort of situation that we can see with the solar system. We must be getting further and further and further away from most of the mass which is holding the stars in orbit, and so we would expect the velocity of those stars to start to decrease. That dotted line shows you what you would expect for star velocities once you get beyond, let's say, 15,000 light years. Now, it's a little bit difficult to measure stars that far out because there are so few of them. You can see that most of the stars are within the red outline, and if we want to get out here at 20,000 or 25,000 light years, there are very few stars we can choose to see what happens to the velocity curve. So actually what is done is not look at stars, but look at hydrogen atoms. Hydrogen atoms will go round the galaxy just like a star goes round the galaxy, and that depends on the mass of the galaxy. It's got nothing to do with the mass of the object itself, not the mass of the star, not the mass of the atom. So we can take over from stars and start to plot out what the hydrogen gas is doing, and if all of the mass is inside that red outline, we would expect that curve to start to come down, just like we see with Jupiter and Saturn and Uranus and Neptune in the solar system. But what we actually see when we measure this is the velocities get higher and higher and higher, or at the very least they flatten off. What they don't do is come down the way we would expect if most of the mass was concentrated in the visible part of the galaxy. This particular plot, velocity as a function of distance, is called a rotation curve. And these rotation curves have been measured for a large number of galaxies, and it is often found that the curve flattens or increases. The curves do not come down the way we would expect in the vast majority of galaxies that have been studied. So if objects a long way from the galaxy are moving really fast, the gravity must be a lot stronger than we can account for simply by looking at the size of the galaxy. There's the expression again. It's as if there is some additional mass that is not luminous, it's not taken into account by looking at the stars and the gas. Something is providing the extra gravity that is needed to keep the stars or the gas orbiting at such high velocities, even when they are a long way outside the visible edge of the galaxy. it looks like we have another piece of evidence for something which we can call dark matter. So that's the second piece of evidence, and I'll give you a sort of cartoon of one way of thinking about that. If we imagine the stars going around a galaxy, this is just a short video clip which repeats every few seconds. You can see the stars close to the centre are moving quite fast, and the stars around the edge are moving quite slowly, as indicated by that little graphic at the bottom which says the velocity as a function of distance is quite high close to the centre, and then it falls away, much like a planetary system. But what we actually observe is more like the cartoon on the right. Yes, the stars close to the centre are moving quite fast, but the stars at the edge are also moving quite fast, a lot faster than you would have thought. We would expect to see galaxies like on the left with the outer stars moving slowly, but what we actually observe is the outer stars are moving much faster than we can account for unless we assume the existence of dark matter. Let's have a think about a third strand of evidence. Now this one is called gravitational lensing. It's rather unlike the previous two. Previous two were talking about what's keeping galaxies together. The second one was what's keeping stars together. This one is looking at calculating mass from its gravitational effect, not on galaxies in a cluster, not on stars in a galaxy, but on light itself. Yes, I know that I've said that dark matter does not emit light and it does not absorb light. That is correct. But if dark matter has mass, which it must do, it produces gravity, and gravity can bend light. Or, if you prefer, gravity distorts space and light follows the curves of space. That's a slightly different way of looking at it. So this is what we mean by gravitational lensing. What we have here is a distant galaxy at some point, and light is travelling from that distant galaxy to Earth. But on the way, it passes through a large galaxy cluster. And this galaxy cluster is massive enough to distort space so that not only does light travel in possibly a straight line from the distant galaxy to Earth, it is also possible for the light to follow curved paths because the galaxy cluster has distorted space. And so what we can get is a sort of a focusing effect where light takes different paths from the galaxy to reach Earth. And so a distant galaxy might be imaged more than once. And as indicated in the top left corner, a distant galaxy, which might be virtually a point source because of its distance, because of this effect of the focusing of this large massive object, this galaxy cluster, in between us and the galaxy, it can result in the galaxy itself being imaged not as a small round object like this, but a much magnified and quite often quite distorted version of that same galaxy. So here we see a lensed galaxy, meaning the galaxy as it would appear having passed through this gravitational lens, distorting the light because of the mass of the galaxy cluster bending space, which then bends light. We can see lots of evidence for gravitational lensing. For instance, here there's a rather distant, rather bluish galaxy, in which it happens to line up by pure coincidence with a foreground object. The rather orangey object here in the foreground is a galaxy which is bending the light from the more distant blue galaxy. It's distorting that blue galaxy so much that it doesn't appear like a normal spiral galaxy. It appears to have been distorted into almost a circle, a huge horseshoe shape. You can actually see how that might come about by looking at a rather crude version of a lens. For instance, if we take a light source such as a distant candle, again, let me just get rid of the controls. If we see a light source such as a distant candle, and we look at that light source through the base of a wine glass, we can see that the candle actually appears as multiple light sources. And in the bottom right, we can see the light sources have been distorted. The candle has been stretched out into a little bit of an arc on two sides of the base of the wine glass. And on the left hand side we can see that if the lens is in just the right orientation and just the right position, then the distant light source actually gets imaged as an entire circle, which explains how we might get a horseshoe shape for imaging a very distant galaxy. So in other words, the base of the wine glass made of glass is distorting the view in much the same way of a galaxy cluster distorting the view of more distant objects. And we can see, for instance, one example, this is one example of many, of a galaxy cluster. Again, these rather yellowish objects are objects that are relatively close to us, and these orange and blue objects are in the distance, and they are being distorted by the light passing through this galaxy cluster. So you can see these galaxies are getting distorted, and you've got these lines and you've got these streaks, and the more you look, the more of these streaks you see, and you realize that you're getting a very distorted view of more distant galaxies because of the light traveling through this galaxy cluster. Now, it's not easy to do, but the distorted images can give us information about the mass of the objects in the lens. In other words, we can say for a given mass, how does that distort space and how does that result in gravitational lensing? It's tricky to do it backwards. In other words, it's tricky to say, given this amount of a distortion, given these images of distant galaxies, can we work out what the mass has to be in order to give that degree of distortion? It's tricky, but it can be done. And when theorists calculate how much mass is responsible for these distorted images, then it is found that there's far more than can be accounted for simply by looking at all the galaxies that appear to be part of that cluster. Yet again, it's as if there is more additional mass that is not luminous, that's providing the extra gravity that is needed to bend the light and to produce the distorted images that we see. Not just in one or two clusters, but of the hundreds of clusters that have been imaged, in all cases it looks like there's more mass than we can account for just by looking at the stars in the galaxies. So that was three separate strands of evidence. There is a fourth strand of evidence based on the cosmic microwave background, which I'm not going to cover here for brevity, but it is in the handout if you want to look at that. So, I hope you're convinced that there is evidence, there is observational evidence that something is wrong, and there appears to be much more mass out there than we can account for from what we can see. The question is, what is it? There are two principal lines of thought, two candidates for what dark matter might be. So-called MACHOs, massive astrophysical compact halo objects, and WIMPs, weakly interacting massive particles. Let's look at both of those. It's actually historically WIMPs that came first, in the sense that the idea of weakly interacting massive particles, which I'll explain in just one moment, came about, but then people said, well, I'm not going to do research on WIMPs, that doesn't sound very masculine. I'm going to look at different objects. I'm going to look at, what's the opposite of a WIMP? A MACHO. And then it was reverse engineered to actually come up with the acronym Massive Astrophysical Compact Halo Objects. So what does that acronym actually mean? Objects, okay, objects. Astrophysical, it means there's something out there, something like, stars or planets that are actually responsible for the dark matter. Massive, well, they have to be massive in order to give us the effects we're looking for. What do we mean by compact and halo? Compact, we haven't seen these objects, so they are presumably quite small objects. What do we mean by halo? Well, it is thought that they're in the halo of a galaxy. The halo of the galaxy is a large sphere with the galaxy at the centre. The galaxy contains lots of stars, lots of gas, lots of dust, and the halo is a large sphere that encompasses all of that and could be substantially larger than the galaxy itself. So a halo object is an object in the halo of the galaxy, a bit like globular clusters are in the halo of the galaxy. So one question is, well, what could they be? Well, the thought is that maybe they're just ordinary objects in the sense that they're made of ordinary matter that does not emit any light, so we haven't actually counted it when we look at a galaxy and try and work out how bright a galaxy appears to be, and hence how massive it is. Maybe we're ignoring the fact that there are a lot of dark objects out there, dark in the sense that they do not emit light. They are ordinary matter, but for some reason or another they don't emit much light. For instance, black holes, neutron stars, or even white dwarfs. You might think that sounds a bit off, because surely a white dwarf is a rather bright object. It's white hot and it's irradiating light. Well, yes, a white dwarf, when it's born, when the sun comes to the end of its life, it's going to become a red giant. The outer atmosphere is going to be blown away, and the core of the star that's left is then called a white dwarf. But there's no longer any nuclear fusion reactions going on, and therefore a white dwarf will slowly, simply cool off, because it's not generating any internal energy. So a white dwarf starts white, but given a little bit of time it will fade away and ultimately become invisible, because it simply won't be radiating any visible light. So maybe black holes or neutron stars or white dwarfs, relatively small objects that can't be seen easily, maybe they are responsible for the dark matter that we're missing. So if they are too faint to be seen, then how can we possibly detect them? If the hypothesis is maybe they're there, what do we need to do to find them? And the answer lies in gravitational lensing again, but not lensing from a huge object like a galaxy cluster. We're talking about lensing from small objects such as individual stars, and that's called microlensing. How does that work? Well, let's imagine we have a star as shown by this left-hand panel, and the star sends out light and some of it arrives at Earth, and so we measure a certain amount of light arriving. If it just so happens that every once in a while a compact object might drift in front of that star, then that star will be sending out light in various directions. If an object, let's call it a black hole for the sake of argument, if a black hole happens to drift into our line of sight of a distant star, then that black hole can distort the space around it and produce this lensing effect and start focusing some of the light onto us, onto our telescopes at Earth. And hence the star could, for a little while, appear a little bit brighter because of this focusing effect. But it will only last for as long as this black hole happens to be in our line of sight. If that black hole drifts away, the star will go back to its original brightness. So if we were to stare at a star and it seems to be the same brightness, but then for a little while gets brighter and then goes back to its original brightness again, that's not normal behavior for a star. So maybe that's an indication that an unseen object has drifted into our line of sight. That's not very likely, so there's no point in doing an experiment in which you just stare at one star and see what happens. It's unlikely to happen with a single star, so the best thing to do is to look at lots of stars at the same time and see if it happens on a number of these objects. So that experiment was done a little while ago. This is an image of the Milky Way, of course taken from the inside, because we are inside the Milky Way. But if you imagine for the moment that this is a picture of the Milky Way seen from the outside, then we have a bright central bulge in the Milky Way, and we also have a couple of small satellite galaxies, the Large and the Small Magellanic Clouds. So if you imagine that we are in the main part of the galaxy, if we were to look at the Large Magellanic Cloud, in between the LMC and us, there's a little space here which is part of the halo of the galaxy, and if there are black holes all over the place, if there are large numbers of them, which there would have to be if they're an explanation of black holes, if they're an explanation of dark matter, then these black holes would have to be all over the halo of the galaxy, and some of them would be drifting around in between us and the Large Magellanic Cloud. So that was the experiment that was done. Look at the stars in the Large Magellanic Cloud, stare at them for a long time and see how often you get a star that suddenly brightens, indicating that a massive object like a black hole or a neutron star happens to have drifted past. That experiment was done for quite a few years, and yes, quite a few black holes were discovered this way in the halo of our galaxy. But not enough. Machos are definitely out there. Massive, compact objects are floating around in the halo of our galaxy. But there's not nearly enough of them to explain the amount of dark matter that exists. Remember, dark matter is more massive than all of the ordinary matter put together. The sheer number of black holes that would be needed would be vast, and there doesn't appear to be anything like the right number to explain dark matter. So machos were put forward as a hypothesis. It doesn't look like they can explain dark matter. So then we come back to the second option. Maybe dark matter is made up not of black holes, but of WIMPs, weakly interacting massive particles. In other words, particles that do interact through gravity, but don't interact through electromagnetism. They're not charged particles. They're not like electrons or protons. They don't have a charge, but they do interact through gravity. They have a mass. They are massive particles. But weakly interacting means they don't strongly attract each other like electrically charged particles do. They interact through gravity, essentially gravity only. In that sense, they're similar to neutrinos, a particle which I haven't really described, but neutrinos are particles that interact through gravity but not through electromagnetism. But WIMPs would have to be much heavier. Neutrinos are too lightweight to explain dark matter. So maybe WIMPs are similar to neutrinos, which we already know about, but they must be much heavier and probably moving more slowly. Presumably they must have been born in the Big Bang. It's difficult to see how they came into existence after the Big Bang. So they were born in the Big Bang, and every particle that we know of seems to have an antiparticle. Electrons have anti-electrons, protons have antiprotons, quarks have antiquarks. Every particle seems to have an anti-equivalent. It's a sort of mirror image, if you like, with an opposite electrical charge. So if we did make dark matter particles in the Big Bang, it's thought that there will be anti-dark matter particles as well. And just like an electron can annihilate with an anti-electron and produce energy, it's thought that dark matter could annihilate with anti-dark matter. But we don't see much evidence of that, but maybe it is going on. Maybe WIMPs, maybe there aren't many of them around, but if they interact through gravity, perhaps WIMPs would prefer to be somewhere where there's a lot of gravity. For instance, what about the heart of the sun? Maybe the sun is full of WIMPs. That's a thought. Okay. If that's the case, then it might be that in the heart of the sun, a load of neutrinos are being made that can't be explained through the processes of nuclear fusion, which is generating the energy of the sun. So let's see if we can find an experiment that tells us what neutrinos are coming out of the sun. Neutrinos are travelling very quickly, and one way of detecting them is to build a large water tank. That sounds rather weird, that you build a water tank to find a very energetic, very fast-moving subatomic particle. But the principle is that, for instance, you know about a fighter jet like this, moving through the air faster than the speed of sound, will produce a shockwave and a sonic boom. And a sonic boom is the result of an object moving through air faster than sound can move through air. And that's what we're seeing here, the shock wave. And of course what you would see is what you would hear is the sonic boom. Well, there's an analogue with light. If a particle moves through a medium faster than light can travel through that same medium, then we get the equivalent of a sonic boom, but in the optical spectrum. We get a flash of light. Remember, nothing can travel faster than light through space in a vacuum, but when you're travelling through water, for instance, it is possible for the particle to travel through water faster than light can travel through water. And we can see that, for instance, if you look at what's going on in a nuclear reactor. This is surrounded by water. This eerie blue glow is not something that's been added as a special effect. That's what it actually looks like, because particles are now coming out of this nuclear reactor and they are travelling through the water faster than light can travel through the water, and that produces this optical equivalent of the sonic boom. It's a blue flash of light. So there's lots of blue light in the water because of the very fast moving particles in the water. So that's what is being looked for, a large tank of water such that if we have a fast particle moving through the water, it'll produce light, and most of that light will be beamed in the direction it's travelling. This particular type of light is called Cherenkov radiation. So if you switch off all the lights and have a load of photodetectors around the outside of this tank, if you see a blue flash of light, that means you've seen the flash telling you that a particle has moved through this tank. And you can see that if the light is shining in the direction it's travelling, some of the photodetectors will pick up the light and some won't. So by looking at which photodetectors trigger, you can tell where the particle came from. And knowing the time of day, you can work out whether or not it's come from the direction of the sun or not. And that will tell you if you're picking up these mysterious neutrino particles coming from the sun. Now, it's a very large tank. You can just about get the scale from the fact that there are some people in this little cartoon here. Another way of getting the scale is to look at what happens when they take the water out and they have to go and do some maintenance on the photodetectors, which are these sort of football-sized objects that are covering the entire inside of the tank. With the water level down, it's possible to do some maintenance, and if you can't quite see what's going on in the middle of the image, that is two men in a dinghy. So you can see just how many detectors there are. Once they've done their maintenance, the tank will be refilled with water, the light switched off, and then they wait for the blue flashes. That's an indication of what the photodetector is. Basically, it's a light detector tuned for looking at very brief flashes of blue light and the associated electronics. You don't have to use a water tank. There are other experiments which are going on for looking at dark matter. For instance, there's one at the South Pole. And here there's a laboratory. The laboratory is called Ice Cube and it's sitting on top of the Antarctic ice cap, but that's not where the detectors are, that's just where the laboratory sits. The detectors are on cables which are strung below the top of the ice cap. Remember, on the Antarctic landmass, there's something like 2 to 3 kilometers of ice. And so these detectors are placed a long way down below the top of the ice cap. Just to give you scale, let me just show you that's the Eiffel Tower to the same scale. So effectively we have a detector which is a block of ice. Any particles travelling through this block of ice will produce a blue flash which is picked up by the detectors, which are strung like a string of pearls on these cables dropped from the surface. Roughly speaking, the cube of this experiment is 1 kilometre by 1 kilometre by 1 kilometre block of ice, which is why it's called the Ice Cube experiment. The particles don't really care if they're moving through water or whether they're moving through frozen water. The same physics applies. So this is an experiment which is ongoing to again measure neutrinos, and those can be used to see if there's any evidence for dark matter particles concentrated in the centre of the sun. But as well as perhaps being located in the centre of the sun, where's another place where gravity is very strong? As well as the centre of the solar system, well, the centre of the galaxy has a supermassive black hole. Some millions of stellar masses are concentrated in a small area. So maybe, if WIMPs do exist, they would like to collect in that area. So maybe there's a lot of WIMPs at the centre of the Milky Way. It is thought that maybe, if there are lots of WIMPs in the centre of the Milky Way, they might produce a lot of gamma rays. And so there are experiments to search for the gamma rays that appear to be coming from the direction of the centre of the Milky Way. So remember, the centre of the Milky Way, which is indicated here in this sort of all-sky map, that is rather low down in the south, as seen from the United Kingdom. If you want to pick up what's going on from the centre of the galaxy, you would put a detector not in the UK, you would put it in the southern hemisphere. So there are plans to build a so-called Cherenkov telescope array. This artist's impression implies that it's going to be in Monument Valley in America. No, that's just an artist's impression. This is going to be built in the southern hemisphere, and lots of these telescopes are going to look into the sky. They're not going to be looking necessarily in the direction of the galactic centre. What they're doing is looking for any particles that are coming into the Earth's atmosphere, and in a sense the entire Earth's atmosphere is going to be used as the detector. They're looking up to see if there are any blue flashes as a result of very energetic particles being generated, for instance, by gamma rays that might be the result of the existence of dark matter at the centre of the galaxy. Very energetic particles in the atmosphere can move faster than light can travel in the atmosphere and can produce the characteristic blue flash, which can then be picked up by some of the telescopes in the array. Some telescopes will see it, other telescopes won't. That gives you a certain amount of directionality, which tells you from which direction did this particular particle appear in the first place. In other words, did it come from the direction of the centre of the galaxy? So a number of different large-scale, relatively expensive experiments to look for dark matter. But there are other ways of doing it as well. You can do WIMP detection. You can build detectors that might be able to detect the existence of WIMP particles on a much smaller scale. So for instance, there are some here which I've listed. The acronyms are given in red on the left-hand side, simply so that if you're interested, you can go away and look them up and you can find out what these various experiments are doing. But as indicated on the right-hand side, these are small-scale experiments, literally benchtop type experiments. For instance, if a dark matter particle does come screaming into the Earth's atmosphere, is it possible that it goes into this detector and bangs into an atom which then recoils as a result of a dark matter particle coming in? Is it possible to measure the recoil of an atom which tells us that a dark matter particle has come through our experiment? Well, a number of these experiments, perhaps dozens of them, just a few of them indicated on the left-hand side there. Lots of them are running, lots of them have seen something, but many of the observations so far, many of the events that they have recorded are either perhaps contradictory or at the very least not yet confirmed to be dark matter particles. More time is needed, and a number of these experiments need to give us data across the world before we can be convinced that we are indeed finding a dark matter particle. So we might be getting results in years to come from some of these experiments. But there are alternatives. There's another possibility, and some people believe that we've simply misunderstood how gravity works. In other words, we seem to be missing a lot of mass, but that's because we've done all of our calculations incorrectly. In other words, we only seem to need dark matter, but maybe it's a consequence of the fact that gravity works differently on different scales. Newton came up with the law of universal gravitation. The gravity that's pulling my mug down to the desk is the same gravity that's keeping the moon in orbit. It's the same gravity that's keeping the sun going around the galaxy. It's the same gravity that's holding the galaxies together in a cluster. But maybe that assumption is wrong. Maybe gravity works differently on the largest of scales compared to the scale of a galaxy, compared to the scale of a solar system, compared to the scale of an experiment done on planet Earth. If gravity works differently on different scales, then it can be found by jiggling the equations that we don't need dark matter. This approach, basically saying Newtonian mechanics is wrong, it's called modified Newtonian dynamics, or MOND. And yes, if you modify gravity, you can get rid of the need for dark matter. The problem is, by modifying gravity, you get a shed load of different problems that you then have to deal with. So it solves one problem, but generates a dozen more. So no one yet has come up with a theory which gets rid of the need for dark matter and doesn't have all sorts of its own problems. So in that sense, the jury is still out. Does it actually matter? Who cares if galaxies seem to be rotating at a speed which isn't quite what you would expect them to be? What are the consequences? Well, the biggest consequence is the fact that if you want to understand how the universe came to be the way it is, in other words, if you run a simulation of how did we go from the Big Bang to where we are now, if you want to explain the observation of galaxies are distributed throughout the universe in a certain way, then you need to do a simulation, and you can't afford to ignore dark matter. Without dark matter, the simulation of how did we get to be where we are now simply do not work. If we start with the assumption that everything that is currently inside the observable universe used to be a lot closer together, so we're talking about the observable universe, a sphere which is some 100 billion light years across, all of that used to be in a volume approximately the size of a golf ball. That takes a little bit of imagination, you must admit, but if the universe was very small in its early days, well, it wasn't perfectly uniformly dense or uniformly temperature distribution across the entire universe. There were small variations which I like to think of as being the dimples in the golf ball. Those dimples, those small, tiny variations in density, when you let gravity take hold, gravity takes hold of those small differences and produces the sort of universe that we see. In other words, if we run a simulation, if you want to know more about these simulations, the web page is at the bottom of the page here. Then if we run, let's take a chunk of the universe, let's give it a small variation of density and let gravity do its thing over a few billion years. What do we see? We see the formation of filaments, we see the formation of voids, we see a cosmic web structure, and where these filaments cross each other we get little dense regions. This is where galaxies form, this is where clusters of galaxies form. When we look out into the universe, we don't see galaxies uniformly distributed over the entire universe. We see them clumped together. We see these structures, we see these filaments, we see these voids. But this simulation, let me just run that again, this simulation of what we would expect the universe to look like only agrees with what we observe if the simulations include a large amount of dark matter, more dark matter than ordinary hydrogen and helium that we think existed in the very early universe. Without dark matter, the universe doesn't clump enough. 13.8 billion years, the current estimate for the age of the universe, isn't long enough to make galaxies if we don't have dark matter. It is thought that the dark matter collapsed under gravity and formed these filaments and voids and structures, and then ordinary matter, all of the hydrogen and helium, piled in on top of the dark matter. Without dark matter, you can't make galaxies, you can't make stars, you can't make planets, you can't make us. So yes, it quite definitely matters. On the largest of scales, the universe looks reasonably uniform, but quite foamy in structure because of this web-type structure. And if we zoom in on different parts at different scales, we start to see the structures within these filaments, the galaxies, the galaxy clusters, etc. So what have I been talking about? I've tried to explain that dark matter interacts with light in a different way to ordinary matter. I've shown you 3 strands of evidence that dark matter exists. A 4th one is in the handout if you want to go and look at it. We don't actually know what dark matter is. It might be machos, black holes and small compact objects. It might be WIMPs, particles that we simply have not found yet. The evidence indicates that it's not machos. So therefore we're left with, it's a particle that we haven't yet found. Despite extensive searches for many years, and despite people combing through the Large Hadron Collider data, looking for signs of what have we missed. We know about this particle and that particle, but what particle is missing that would explain anything that we can see in the data? So far, no evidence that such a particle exists. And does it matter? Well, I've tried to explain that with cosmic evolution, at the moment the simulations in a computer would tell us that we cannot explain how the universe came to look like it does now over the 13.8 billion year history of the universe without dark matter first producing all of the structures which ordinary matter then piled on top of to produce galaxies, stars, planets, and us. So does it matter? Well, without it, I wouldn't be giving this talk, and there would be no one to listen to this talk. So yes, it quite definitely does matter. Thank you all for listening.